Transitive property of similarity. Welcome, everyone. Today, we are going to dive into a very specific and powerful property in geometry known as the transitive property of similarity. Now, before we get into the new material, let's quickly recap what we already know. In our previous lessons, we established that similarity is a relationship between two figures where they share the exact same shape, even if they aren't the same size. Think of it as one figure being a perfectly scaled version of another. As we move through today's lesson, you'll see that this relationship isn't just a one-to-one connection. It has a very important characteristic called being transitive. This means the relationship can carry over through a chain of different figures, which is exactly what we are going to explore and prove in the next few slides. Understanding the transitive property. Now that we've established that similarity is all about maintaining the same shape regardless of size, let's dive deeper into what it actually means for this relationship to be transitive. In mathematics, we use the term transitive to describe a relation that carries over from one element to another. Think of it like a chain reaction. Specifically for similarity, we can state the property like this. If we have a polygon, let's call it P1, that is similar to a second polygon, P2, and that same polygon, P2, is also similar to a third polygon, P3. Then it follows logically that the first polygon, P1, must also be similar to the third polygon, P3. To make this even clearer, we can write this out using mathematical symbols. We represent similarity with a tilde symbol, so we would say, if P1 is similar to P2 and P2 is similar to P3, then P1 is similar to P3. In the next few slides, we are going to break down the logic behind why this chain of similarity works so perfectly by looking at the angles and the side ratios. Step-by-step logical breakdown. Now, you might be wondering, how do we actually prove that this property works? It isn't just a random rule, it follows a very logical path. To understand why this property holds true, let's break it down by looking at the two fundamental conditions that define similarity in the first place: having equal corresponding angles and having proportional corresponding sides. In the next few slides, we are going to examine these two conditions step by step to see how they carry over from one polygon to the next. Relationship between P1 and P2. Since P sub 1 is similar to P sub 2, we can rely on the fundamental rules of similarity that we've studied before. First, this means that all the corresponding angles of P sub 1 are exactly equal to the corresponding angles of P sub 2. Second, it means that the ratio of the corresponding sides of P sub 1 to P sub 2 is a constant value, which we will refer to as K sub 1. Now that we have established the definition of the transitive property in the previous slides, let's look at the first piece of our logical breakdown. On this slide, we are focusing specifically on the relationship between our first two polygons, P1 and P2. Keep this constant ratio in mind, because in the next slide, we are going to see how a second ratio, K sub 2, enters the equation to help us link everything together. Relationship between P2 and P3. Now that we have established the relationship between the first two polygons, let's look at the second pair. Moving on to slide 5, we examine the relationship between polygon 2 and polygon 3. Since polygon 2 is similar to polygon 3, the same rules of similarity apply here. This means that the corresponding angles of polygon 2 are exactly equal to the corresponding angles of polygon 3. Furthermore, just like we saw in the previous slide with the first pair, the ratio of the corresponding sides of polygon 2 to polygon 3 remains a constant value, which we will refer to as K sub 2. Keep these two relationships in mind, because in the next slide, we are going to link all of this together to prove the final connection. Establishing the relationship between P1 and P3. First, let's look at the angles. From our previous slides, we know that the angles of polygon P1 are equal to the angles of polygon P2, and we also know that the angles of polygon P2 are equal to the angles of polygon P3. Because of the transitive property of equality, which you might remember from our earlier lessons on basic algebra. If the first set equals the second, and the second equals the third, then the angles of polygon P1 must, without a doubt, be equal to the angles of polygon P3. Next, let's examine the sides. In slide 4, we define the ratio of the sides of P1 to P2 as a constant, K1. In slide 5, we saw that the ratio of the sides of P2 to P3 is another constant, K2. If we combine these, the sides of polygon P1 are K1 times the sides of P2, and since those sides are K2 times the sides of P3, the sides of P1 are actually K1 times K2 times the sides of P3. Since multiplying two constants always results in another constant, we have maintained a proportional relationship. So, to conclude our proof, because we have successfully demonstrated that both necessary conditions, equal corresponding angles and proportional corresponding sides, are satisfied, we can officially state that polygon P1 is similar to polygon P3. This confirms that the property of similarity is indeed transitive. Now that we have looked at the individual relationships between the first two pairs of polygons in the previous slides, let's bring it all together to establish the relationship between the first and the third polygon. This is the core of our logical proof. Real-world example, digital image scaling. Now that we have established the mathematical proof behind the transitive property, let's step away from abstract polygons and look at how this concept actually functions in your everyday life. To do this, I want you to consider the common process of resizing a digital photograph on a computer. Scenario. Now, let's bring this mathematical concept into a practical, real-world context to see how it actually works in your daily life. Imagine you are working with digital images on your computer. Suppose you start with an original, high-resolution photograph, which we will call image A to save space. You create a much smaller, scaled-down version of this photo to use as a thumbnail, and we'll label this version image B now. Later on, you decide to take that same small thumbnail, image B, and enlarge it to create a medium-sized printed photo, which we will call image C. Keep these three distinct stages in mind, as we are about to analyze the geometric relationship between them. Step-by-step analysis. Now, let's apply everything we've just discussed to a practical, real-world scenario to see this property in action. Let's look at the step-by-step analysis of our digital image scaling example. First, let's look at the relationship between image A and image B. When you take your original photo and create a small thumbnail, the software performs a uniform scaling. This means it shrinks the image without stretching it horizontally or vertically. Because the scaling is uniform, the proportions remain exactly the same, and angles at the corners of the image boundaries remain 90 degrees. Therefore, we can say that image A is similar to image B. Next, we move to the relationship between image B and image C. In this step, you are taking that small thumbnail and enlarging it to create a medium-sized print. Just like before, the software scales the image up uniformly. Once again, the proportions are maintained, which means image B is similar to image C. Finally, let's look at our conclusion. By applying the transitive property of similarity that we studied earlier, we can see that because image A is similar to image B, and image B is similar to image C, the final print, which is image C, is automatically similar to the original photo. Image A, if you look closely, you'll notice that the actual shape of the person or object in the photo hasn't changed at all. The only thing that has changed is the scale. This perfectly demonstrates how the property carries the relationship of similarity through the sequence. Key takeaways. First, let's revisit the formal definition. As we've seen throughout this presentation, the transitive property states that if polygon P1 is similar to polygon P2, and polygon P2 is similar to polygon P3, then it follows logically that polygon P1 is also similar to polygon P3. It's that direct link that allows us to bridge the relationship between the first and the third figure. Second, it is important to recognize the concept of consistency. This property is vital because it ensures that similarity remains a consistent relationship, no matter how many figures we link together in a chain. Whether we are scaling images down like we saw in our digital photo example, or scaling them back up, the fundamental shape remains preserved across the entire sequence. Finally, remember the essential requirement for this property to hold true. We cannot simply rely on one aspect of similarity. For the transitive property to be valid, the similarity must be maintained through both the equality of corresponding angles and the proportionality of corresponding sides at every single step of the process. All right, let's wrap up our discussion by reviewing the key takeaways from today's lesson. Now, before we finish, I want to point out a few common pitfalls to avoid when applying this property in your homework or exams. Common mistakes to avoid. First, be careful not to confuse similarity with congruence. I often see students assume that if figures are similar, they must also be the same size. However, remember what we discussed at the very beginning of this lesson. Similarity is all about the shape, while congruence requires both the shape and the size to be identical. The transitive property of similarity allows the scale to change as long as the proportions remain constant. Second, avoid the mistake of assuming that only one condition is enough. You might be tempted to think that if only the angles are equal across polygon 1, polygon 2, and polygon 3, then the figures are automatically similar. But, as we broke down in our logical proof earlier, similarity is a two-part requirement. You must ensure that both the equality of angles and the proportionality of sides are maintained through every step of the relationship. Finally, always pay close attention to the order of correspondence. When you are applying the transitive property, you must ensure that the vertices are matched correctly. For instance, if vertex A corresponds to a prime, and a prime corresponds to a double prime, then you must conclude that the correspondence for your final result is vertex A to a double prime. If you lose track of which vertex matches which, your entire similarity statement will be incorrect. Now, as we wrap up our lesson, I want to highlight a few common pitfalls. It is very easy to make certain errors when applying the transitive property, so let's look at these common mistakes to avoid. Keep these points in mind, and you will be able to apply the transitive property of similarity with total confidence.